Okay, so 45, we have two pool balls. I'm going to call this guy ball number 1. This red guy is ball number 1. This 8 ball here is black ball, ball number 2. Ball 1, ball 2. Initially, ball number 2 is at rest. It's just sitting there. And then ball number 1 comes in. The problem doesn't say this, but let's just assume it's perfectly X, right? Nowhere in the problem does it tell us exactly which way it's going. But to make things simple, let's just say the ball comes in the positive X direction. So bam, we have a collision. What do you always think about in a collision? In a collision, momentum is conserved. But what makes this problem particularly tricky? Is it a head-on, one-dimensional collision? After the collision, the red ball goes upward and the black ball goes downward, right? So this is a two-dimensional collision. So the way you deal with two-dimensional collisions is you treat the X direction and the Y direction separately. So I have all the vectors written out here. So look. So ball number 1, they tell us it moves, the way they word it is they say that ball number 1 after the collision moves at 4.33 meter per second at an angle of 30 degrees with respect to the original line of motion. So the original line of motion was like this, right? That was the original line of motion. Ball number 1 moves at 30 degrees from that original line of motion. So what do we have to do to that 4.33 meter per second? We got to break it into what? Components. So we got X component, Y component. Same thing for the black ball, for ball number 2. We have X component, Y component. Hey, will you close that door right there? Go close that. I got to focus here. Okay, so look, I'm going to shrink this down, and we're going to analyze the momentums. So let's grab this. Need some room to do this. Okay, so let's look at our momentums. I'll make boxes here. Another box. So this box here, this represents before collision. This box here represents after collision. So we have before and we have after. All right, before the collision, what's the only momentum we have, X or Y? X. Before the collision, all we have is an X momentum. And by the way, what is that X momentum? Oh, we don't know the mass of the ball, but we do know, it says right here. So we don't know the mass of the balls, but what do we know? The balls have the same mass. So let's just call it M and M. The balls will be mass M. So what's the X momentum before the collision? 5m, right? Mass times velocity. The X momentum before the collision is 5m. Now, after the collision, ball number 1 goes up like this. Ball number 2 goes down like this. And we have information about ball number 1. Let's do this in red. Okay, so we have put in our components. So we got boom and boom and then boom and boom. Okay, so for ball number 1, we know that this is 30 degrees, that was given. That's 30 degrees, and we know that the velocity is 4.33. So what would this momentum here be? So now we're talking momentum. If the velocity of ball 1 is 4.33, what would its momentum be? 4.33 m, right? Because it's just all momentum is you take the velocity and multiply by mass. That's momentum. Okay, guys, can we figure out the X momentum and the Y momentum for ball number 1? Yeah, it's a trig problem, right? We got an angle. We have 30 degrees. We have the hypotenuse. So when you do the trig, you find out that the X momentum of ball 1 is 3.8 2.7499 m. The y component is 2.165 m. Does everybody understand how I did that? Just trig, right? Just find the sides of the triangle. All right, now for ball 2, we don't have very much. In fact, we don't have anything. That angle right there is theta. We don't know what it is. Here, let me make this bigger so you can really see it. Okay, so after the collision, ball 2 goes down like this. Now, guys, how can we figure out what these momentums are? This x momentum for ball 2 and this y momentum for ball 2. Can we figure out what they must be? Well, we don't know if it's elastic yet. That's what part B wants us to figure out. Look, can we find the x momentum and y momentum for ball 2? Somebody say yes. Yes, we can figure it out. So for starters, like look, before the collision, what was our y momentum before the collision? 0. So what must be the y momentum after the collision? 0. So look, ball number 1 has a y momentum, right? So guess what? Ball number 2 must be what? Canceling that. This thing right here has to be 2.165 m the other way. Does everybody understand that? The y momentums have to cancel after the collision. Why must the y momentums cancel? Because we had no y momentum before the collision. Does that make sense? So we now know what that is. Now, how do we figure out this guy? How can we find out the x momentum of ball 2? Well, look, before the collision, what was our x momentum? 5. So guys, what must be our x momentum after the collision? 5. Well, right here we have 3.7499. So what must this guy be? The difference between 5 and that, which comes out to be 1.2501 m, right? So now we figured out the x momentum, the y momentum, just by, the x momentum before the collision must equal the x momentum after the collision. Y momentum before the collision must equal y momentum after the collision. Okay? So now, how do we solve the problem? Well, what they want us to figure out is the velocity. What's the velocity of ball 2 after the collision? So let's start by getting the total momentum. So see this black vector right here? Can we figure out the total momentum for ball 2 after the collision? Yeah, using what? Pythagorean theorem. So do Pythagorean theorem. You get 2.5 m. That's the total momentum of ball 2 after the collision. So now we can figure out the velocity. So for ball number 2, post collision, we figured out the hard part. What's the total momentum of ball 2? 2.5 m. What's momentum equal to? Mass times velocity. So what's velocity going to be? Momentum over mass. So you go 2.5 m. The mass is m. So the velocity must be 2.5 meter per second. And then don't forget the angle, right? How do we get that angle? Inverse trig, inverse tangent. 2.165 over 1.2501. Ba-bam, 60 degrees. So the total answer to part A, ball number 2 is moving at 2.5 meter per second at 60 degrees along 60 degrees from the initial line of motion. Make sense? Okay, now the second question is this elastic? Is this collision elastic? So what does that mean? If it is elastic, what does that mean? Kinetic before equals kinetic after. So here's what you got to do. You got to find the kinetic energy before the collision. Look, what's the only object that has kinetic energy before the collision? Ball number 1. So you go, okay, what's kinetic before? 1/2 m. What was the velocity of ball 1 before the collision? 5 meters per second. So this basically simplifies to 12.5 m, right? Because we don't know the mass. The kinetic before is 12.5 m. All right, kinetic after the collision. How many objects have kinetic energy after the collision? 2. So you got to do both. You got to go. So 1/2 m. Okay, ball number 1 was moving how fast after the collision? 4.33. And then ball number 2, 1/2 m, 2.5 meter per second. So this comes out, guess what it comes out to be? 12.5 m. Look, was kinetic before equal to kinetic after? Yes. So was this collision elastic? Faux shizzle.